Well, welcome everybody to this edition of the Quantum Seminar. We are back after a long break, still on Zoom, and hopefully we can be back in personal lectures, just with Germans and occasionally traveling by Americans next semester, but this time it's completely over Zoom, which is great considering that we have a lot of really nice high-profile speakers from all over the world. So today, Tanya Zelevinsky is starting, and I just came in 15 minutes ago, having not prepared anything. So it's really helpful that she has a nicely written Wikipedia article, which I'm going to read you from now. Tanya Zelevinsky is a professor of physics at Columbia University. Her research focuses on high-precision spectroscopy of cold molecules for fundamental physics measurement, including molecular lattice clocks, ultracold molecule photodissociation, as well as cooling and quantum state manipulation techniques for diatomic molecules, with the goal of testing the standard model of particle physics. Zelevinsky graduated from MIT in '99 and received her PhD from Harvard University in 2004 with Gerald Gabriel there as her thesis advisor. Subsequently, she worked as a postdoc research associate at GILA with Yun Yi on atomic lattice clocks. She joined Columbia University as an associate professor in 2008. Professor Zelevinsky became a fellow of the American Physical Society in 2018 and received the Franz Pipkin Award in 2019. So congratulations on that, and we are very happy that you're kicking off our quantum seminar. Thanks for coming.
Great, thank you so much for the introduction. Yeah, I've never seen that page, but it's good to know. Yeah, it's my pleasure to visit with you, at least virtually, and tell you about our work at Columbia University on ultra-cold molecular clocks and quantum state control of molecules. So as you probably know, quantum science with molecules has really taken off in the last decade or so. It allows us to go beyond cold atoms in gaining various insights into fundamental chemistry processes, into designing and engineering quantum materials with various long-range interactions, and designing quantum information systems as well. And also molecules help us come up with new and enhanced platforms for measurements of fundamental physics, which has been a particular interest of my research group. So why do we like our molecules to be ultra cold? And really, what temperatures do we have in mind in order to do quantum science? Well, this really comes down to the ability to control the full array of molecular quantum states. And molecules have quite a wide range of energy scales. And this makes them interesting, but also makes them more complicated. So for example, the typical electronic energies are in the visible or infrared, which would correspond normally to thousands of Kelvin. Then going down in energy, we have vibrations, and these could be hundreds of Kelvin. And then rotational and hyperfine energies are smaller, down to fractions of a Kelvin. And in order for us to achieve a good resolution of all these states, and also ideally to be able to hold the molecules in a versatile optical trap, and those have typical depths of about 10 microkelvin, that means the translational energies of the molecules should ideally not exceed the microkelvin scale. So creating these ultra cold samples of molecules is our first step to using them both in metrology and in fundamental chemistry. And here are a few questions that we address through the research that we'll discuss today. So we would like to understand if small molecules can contribute to our understanding of fundamental forces. And this includes new, sort of still undiscovered physics, but also old physics like QED, which still plays a really important role in how we understand atomic and molecular structure. So we are exploring whether it's possible to control molecular states across a large range of the electromagnetic spectrum, including the terahertz region, and to decouple these quantum states from their environment. And finally, we're also investigating if there may be a metrological advantage for using molecular versus atomic systems. Of course, the first task of working with ultracold molecules is creating these molecules. And generally, two different pathways can be used to make molecules in the microkelvin range. So one method is to directly cool them, specifically molecules with an alkaline earth metal optical cycling center. So these are metals from group 2. And the metal would be typically bound to a halogen like fluorine, or to hydrogen, or even to a larger functional group, which can give us access to polyatomic molecules. But the second method, the more indirect one, is to laser cool atoms first. And these are usually alkali metals in group 1. And then these ultra-cold atoms are then assembled into diatomic molecules in their ground state by using magnetic fields or laser fields. However, in group 2, the alkaline earth metals in group 2 have many features that are attractive both for laser cooling and for precise metrology. So you will recognize some of these as clock atoms, but these features also transfer onto the bound molecules that are composed of these atoms. Now, the downside is that these atoms don't have unpaired electron spins, and so they're difficult to control with magnetic fields. But we've solved this difficulty by using all optical methods to create ensembles of diatomic strontium molecules in their ground state. So these are fairly unique ultracold molecules with purely van der Waals interatomic potentials. So our strontium dimers are created by optically making excited dimers using or during collisions of ultracold laser-cooled strontium atoms. And then these dimers spontaneously decay to the electronic ground state of the molecule. And since the outgoing photons take away this binding energy gap, it means that the resulting molecules are still at just a few microkelvin and moving at very slow speeds of millimeters per second. The molecules are trapped in a one-dimensional optical lattice, which is simply a standing wave of light. So initially, the lattice tightly holds the atoms in these bright microtraps, or lattice pancakes, as we call them. And then the molecules are also created in the lattice, preserving the original ultra-cold temperature. And then any probing light propagates along the lattice axis to suppress Doppler dephasing. And this is the setup we use to create the strontium molecules by laser cooling an atomic beam that you can see near the top of the picture, and then trapping the atoms in an optical lattice and photoassociating them into molecules. And at least a dozen different laser systems are used for creating, trapping, and probing the molecules. And so in the vacuum chamber that you can see in the inset, there's a fluorescing blue cloud of strontium atoms that is visible by eye. These ultra-cold van der Waals molecules that we make, strontium-2, they have two important features to keep in mind. One feature is the existence of very narrow optical transitions. And the second one is a completely non-magnetic or spinless ground state. Just in case you're interested in more details of the molecules, you can very briefly look at the relevant potentials on the left. So the ground state potential dissociates into a pair of ground state strontium atoms. And the lowest lying then pair of potentials called 0U and 1U has the threshold at the intercombination line or spin flip transition of strontium. So this intercombination line gives rise to the narrow optical transitions in molecules and also provides a very nice handle for quantum state control. The second feature, the relative simplicity of the spinless ground state potential that we have, at least for the bosonic isotopes, is a very big advantage for precise metrology and for ab initio calculations. So to illustrate the point about the ground state van der Waals potential, here you see the ab initio calculated potential, which is shown with red points, and the experimental potential derived from some older traditional spectroscopy, and that's shown with the blue line. And there's a very good agreement at the level of 1%. So I mentioned that the strontium molecules give us access to very narrow optical transitions. And actually, a lot of quantum control can be gained from these forbidden transitions, as well as just insight into basic molecular physics that we can now get at a very high precision. And it's interesting that in addition to the regular narrow transitions, there's also a new type of super narrow optical transition in these molecules, which is totally absent in atoms. And this is the transition to the state with the same inversion symmetry as the ground state, which on the top is labeled as G or gerade even. And this results in two ladders, two families of excited molecular states, where the optical decay pathways down to the ground state will interfere either constructively or destructively. So the regular states, the regular narrow states look like SP plus PS in terms of their wave function and are superradiant, which are still quite long-lived. That's about 10 microseconds, but their decay is electric dipole allowed. And these new states are subradiant of the form SP minus PS with lifetimes that are 1,000 times longer, which is on the order of 10 milliseconds. And the transition mechanism is magnetic dipole. So these subradiant states that are really, we can resolve them at the tens of hertz in the optical regime. They give us more opportunities for optical control of the quantum states of the molecules. So here on the left, we see coherent optical Rabi oscillations. And then on the right is the long measured lifetime that's approaching 10 milliseconds for one of the subradiant states. And these various long-lived excited states also present interesting opportunities for metrology that we're looking into.
Why are you calling it subradiant and superradiant? I mean, like subradiant and superradiant, I always associate with some sort of collective effect. But yeah, I don't think that you mean that, right?
It's a two-body, you can think of it as two-body subradiants and superradiants. I think conceptually it's similar. So the electric dipole decay interferes destructively or constructively, but it's a single, I mean, it's a two-body effect, which means it occurs in a single molecule.
Okay.
Yeah, you don't need other molecules in order to observe this. So these, what I call subradiant, very narrow states are really extremely useful for working with molecules that are trapped in an optical lattice because they can serve as very high resolution probes. For example, we can take a broad spectra of these states and see the expected red and blue lattice sidebands in addition to the narrow carrier transition in the center. And these very direct measurements of the lattice trap frequency allow us to very nicely calibrate the trap light intensity that the molecules see. Also zooming in on the carrier, the central transition and measuring its asymmetric width directly yields the temperature of the molecules. And just jumping ahead here for just a moment, we can also see lattice sidebands with 2 photon Raman transitions. between levels that are just within the electronic ground state of the molecule. So these are terahertz transitions. And in fact, we can hide the sidebands in the what we call the clock mode of operation when we use co-propagating Raman laser beams, or we can, in reverse, we can reveal very strong sidebands in the counter-propagating configuration. So we can then measure the molecule temperature directly without using narrow atomic transitions, while on the other hand, we can suppress the sidebands and any associated line pulling if we want high precision. Okay, so this narrow intercombination transition in general is also a super useful tool for imaging the molecules. And as we discovered a few years ago, also for studying photochemistry in the quantum state resolved situation. So in this case, the optical transition is from a bound state to a continuum where the molecule is split into fragments. So on the bottom left, here's a photodissociation spectrum that is a very sharp step function because it's very sharp because of the long lived excited continuum. So as you go across threshold, you start making fragments very suddenly. And this steep spectrum means that the fragments can be obtained with very little residual heating just above the threshold and below a microkelvin heating. And then the images that you see show the side view of this emerging fragment. But when we image these exploding molecules by looking into the symmetry axis of the trap rather than from the side, we observe these non-classical angular distributions that show very strong matter wave interference. As you can see in these images, one is calculated and the other is experimental. So this type of interference is really a key feature of ultracold reactions in general. And to study this ultracold photodissociation, we simply image the photofragments through absorption. So the molecules are trapped in a small submillimeter region in an optical lattice. And then the photodissociating light is collinear with the lattice, and its frequency and polarization can be varied. And we have a large imaging beam shown in blue, which intercepts the several millimeter area of the emerging fragments, which are shown in green. And this whole thing is absorption imaged on a CCD camera that is looking into the lattice. And so each molecule in the microtrap releases fragments into a three-dimensional spherical shell. And the camera views its two-dimensional projection as kind of shown here. So the typical scale of the images that I showed on the previous slide is about 100 to 200 microns. And all the quantum mechanics of the molecular bond is encoded in this photofragment angular distribution. In other words, the dependence of the photofragment intensity on the angle theta, or also the azimuthal angle phi. Yeah, so here are a couple of specific examples of quantum interference in ultracold photodissociation. So the strontium molecules here are fragmented into their ground state continuum of such that the fragments are simply ground state strontium atoms, and all the quantum states are precisely known, as well as the relative phase between these outgoing quantum states. So in both these cases that I showed here, we are essentially imaging different coherent superpositions of G-wave spherical harmonics, or a relative angular momentum of 4. And this results in the 8-fold fragment patterns. And in each case, the experimental image is shown in the top right of the square, and the calculated predictions are shown in 3 different ways. And so these 8-lobed dissociation images very clearly show the non-classical behavior that results from matter wave interference. And just for comparison, here's what you'd expect from a quasi-classical angular distribution for a dissociated diatomic, which is simply a basic dipolar pattern with the fragments emerging in two opposing directions. And just briefly, I'll also mention that we actually use photodissociation of weakly bound molecules for taking all the spectra that I might show today, including for the molecular clock. So in that case, we just measure the brightness of the photofragments versus the probe light frequency, not worrying about the angular dependence. So this is our basically how we image and how we measure the molecule number. Okay, well, I promised that I would discuss the applications of the ultra-cold molecules to metrology and precision measurements. So in particular, we are developing molecular clocks in our lab. And here's the conceptual implementation of what we call the molecular lattice clock. It involves a pair of vibrational clock states in a molecule that's trapped in an optical lattice, which is just a periodic potential for neutral atoms or molecules. And the two clock states are coherently coupled to each other by a 2-photon transition or Raman transition. And actually the key, the main challenge in designing a molecular clock is also very relevant to designing successful qubits, for example, for quantum information. And this involves maintaining a long-term coherence between pairs of quantum states. And this is the reason to design optical traps that have identical properties and same depths for both quantum states, as you can see is shown here. So these are what we call magic traps. Okay, so then what are the uses of molecular clocks? Well, a molecular clock that's like ours, which provides very precise measurements of vibrational states, actually is an excellent sensor of the interatomic force. So when the bound states of the molecule are known with an uncertainty below a part per trillion, and the interatomic potential and the binding force that holds the molecule together can be reconstructed with this same high precision. And this high precision interatomic force sensing can lead in principle to discoveries of new physical forces. So for example, it may be possible to use molecular clocks to learn about gravity at the ultra short range. So our strontium molecules can be pictured as pairs of atoms separated by their bond length, which depending on the state can vary from about 0.5 to 5 nanometers. And this bond length is set mostly, of course, by electromagnetic interactions between all the electrons and nuclei in the molecule. But since the nuclei are relatively heavy, Newtonian gravity also contributes and makes a very tiny correction to the bond. Then if we have possible deviations from Newtonian gravity, then we can parameterize them, for example, using the exponential Yukawa term with a magnitude A and length scale lambda. And from previous experiments that use various quasi-classical methods, we know that at this nanometer scale, the parameter A has to be smaller than 10 to the power of 22. So in other words, there could be a really huge correction to regular gravity, and it wouldn't contradict any experiment that has looked at specifically at interactions between spinless masses. But the molecular clock is a fully quantum system, which has the potential to go to higher sensitivities. And from the theory point of view, this possible new force or fifth force would be, as I said, a tiny correction to the electromagnetic force. So it's worth to understand the electromagnetic force as well as possible. And so in the basic Born-Oppenheimer picture, the energy of a bound molecule simply consists of the electronic, vibrational, and rotational contributions. Specifically, the strontium-2 ground state has 63 bound vibrational states. And then the energy corrections that go beyond the Born-Oppenheimer include the adiabatic terms. These are proportional to eta, the electron to nuclear mass ratio, as well as the non-adiabatic or eta squared corrections, and various relativistic and QED corrections that depend both on the eta and on the fine structure constant alpha, and also finite nuclear size corrections. And this theory is still very much under development, but we believe it should be possible to describe the leading order corrections almost analytically with coefficients that can be partially fitted to the data. And in this way, isolating mass dependencies that could signal a gravity-like force. So specifically for strontium, it has 3 spinless isotopes that can form dimers of multiple mass combinations, and in total supporting hundreds of clock transitions. And these could provide plenty of information on mass dependence across an order of magnitude of bond lengths. And also, it's nice to know that these various corrections have different asymptotic behavior versus bond length. And this can help distinguish, for example, QED effects from new physics. So yeah, more specifically, the molecular potential energy can be expanded as a power series in the fine structure constant and eta, the electron to proton mass ratio. And so the Born-Oppenheimer energy has superscript 00, and our quantum chemistry colleagues are very busy calculating these terms for strontium-2 molecules. So the status is that the non-relativistic terms, which consist of the Born-Oppenheimer term V00 and the adiabatic correction V01, they have been calculated. And the lowest order mass independent correction V20 is also in pretty good shape. And here I show several different contributions to this term, including mass velocity and the Darwin and spin orbit terms, plus the finite nuclear size correction, which will present its own challenge because of its dependence on the relatively poorly known nuclear charge radius. And these relativistic corrections have been calculated for the tightly bound molecular state and are now in progress for the larger internuclear separations. So going back to the experiment, earlier I described high resolution spectroscopy of molecules that are weakly bound, which is how they're actually created from the laser cooled atoms. But to make the best use of the molecular clock, it's important to be able to create the molecules in the absolute ground state. And in fact, we can now create ground state strontium-2, which is the first ultra-cold molecule of this type. To do this, we just momentarily switch off the optical trap, which then results in very narrow EIT signals like the one shown here. This is electromagnetically induced transparency, where the pump and probe light coherently connect the highest and lowest states in the molecular potential. So you can see a very nice narrow coherence signal, and we can use this nice coherence to implement a steer up or a stimulated Raman adiabatic passage. So initially, all the molecules are in the most weakly bound states, which we call the -1. Then the resonant Raman lasers are smoothly pulsed to transfer the molecules into the ground state, which is V0. We cannot see these deeply bound molecules directly, so we reverse the steer up process and recover the molecules again in the weakly bound state. And from the number of these recovered molecules, we deduce the one-way transfer efficiency, which is currently up to 90%. So here, some details of the ground and excited molecular potentials are shown just in slightly more detail so we can understand the clock scheme. So the clock states 1 and 2 are vibrational levels in the ground state. And here 1 is the most weakly bound state and 2 is deeply bound. These clock states are coupled by this coherent Raman transition through an off-resonant intermediate state. And the frequency of the optical lattice light is shown here with a dashed yellow line. And this lattice can, in principle, couple to some excited molecular state. And all these lasers are phase locked to an optical frequency cone. So we can focus just on the relevant quantum states. In orange and in blue, we have the upper and lower clock states, which here have vibrational quantum numbers 62 and 6. And the lattice happens to be near resonance with a transition from clock state 2 to a deeply bound state in the excited 1U potential. And this state is then highlighted in green. So when the molecules are sitting in the lattice, the clock states, both blue and orange states, are both downshifted in energy, which makes the molecules optically trapped. But generally, the two clock states will see different trap depths, which causes then shifts and broadening of the clock transition. But when the lattice frequency is deliberately blue detuned by a correct amount from the green, this green intermediate state, and that stark shift pulls the blue and green states slightly closer together. And at a specific lattice frequency, the trap depth that I call U here for clock state 2 exactly matches the trap depth for clock state 1. And this is called a magic wavelength, at which the clock resonance sharply narrows, since then both clock states now see exactly the same lattice trap depth. So in practice, one way to search for magic wavelengths is to measure the clock shift, the line shift, versus the trapping light power at various lattice wavelengths, which are shown here in the different colors. And the wavelength with a zero slope will be magic. So this is the red line here. Then as we sweep the lattice frequency through the narrow resonance, we can directly measure the stark shift of the deeply bound clock state 2. So here we change the lattice frequency by about 10 gigahertz around the resonance, and we see the dispersive stark shift curve. And the green bar shows the magic lattice frequency. So it's here exactly at the green line where we expect to see the narrowest clock transition, the narrowest resonance, and the longest coherence time of the clock state superposition. And so here we plot exactly that quantity, the clock resonance line width. And the baseline is quite large because of this lattice-induced broadening, and it even gets worse as we approach the resonance. But at the magic frequency on the blue side of the resonance, it drops quite dramatically, in fact, by over 3 orders of magnitude. So here are a couple of clock spectra on either side of the resonance, but away from the magic frequency. And we see the expected light shifts and broadening from the lattice light, and both are on the order of 100 kilohertz. But at the magic frequency, at the green bar, the resonance is symmetric and it's very narrow. And this is the zoomed in spectrum of the vibrational clock resonance at the magic lattice frequency. So this resonance is 30 hertz wide, which is an improvement of a factor of about 3,000 over a non-magic lattice wavelength. And the actual resonance frequency for this clock state pair is 25 terahertz. So this spectrum corresponds to the quality factor Q of nearly 1 trillion. And I'll also note that the intrinsic clock state lifetimes here are actually extremely long, leading to Q factors that are many orders of magnitude larger. So the metrology is certainly limited only by the technical finesse. This very large natural Q factor comes from this calculation, which shows the intrinsic lifetimes of various clock states as a function of their binding energy in the ground state's molecular potential. And these various contributions include natural decay channels. Also, they include a Blackbody excitation at room temperature. And the net lifetimes that are shown with the gray points, so including all of these contributions, it's the lowest trace. Still, these lifetimes generally exceed 10 to the 5 years. So yeah, very long lifetimes. Okay, and so on one hand, we can use that narrow width of the clock resonance to quantify the coherence of the clock states in the magic lattice, like I showed just now. Or alternatively, we can directly drive quantum Rabi oscillations between the clock states and then measure the duration about these, the duration of these oscillations, which hopefully remains long. So essentially, the molecule is made to oscillate between its tightly bound state and its weakly bound state that has a long bond length. And a well-chosen magic frequency actually helps us reach quite long coherence times for the molecular clock. For example, here we have quantum Rabi oscillations between the molecules or between the molecules and states that are separated by almost 30 terahertz. So this oscillation decays with a long time constant of over 100 milliseconds. Now, for this decay time scale, we are not yet limited by the two-body collisional lifetime of the molecules, which is shown here with the purple triangles. But instead, we're currently limited by the lattice-induced loss of the molecules that happens in the lower clock state, and this is shown here with the red line. So the lattice at the magic wavelength, because it's near resonance, still induces some amount of scattering that we see here. In fact, unfortunately, somewhat more scattering than what we expect, and we are still trying to understand that. But the nice thing about molecules is that they offer multiple choices for magic wavelengths because they have so many states and so many transitions. And we can see if we can choose one that leads to a better coherence. And to do that, we looked at a plot like this, which uses colors to show the coupling strength or transition dipole moment squared, DMS, between the ground state vibrational levels on the vertical axis and the 1U excited states on the horizontal. And the brighter colors indicate a stronger coupling. So here we see a typical pattern with two main branches, which and the structure arises because, of course, the molecule spends the most time at its inner and outer classical turning points. And generally, as a sort of a rule of thumb, the best magic wavelengths correspond to the stronger couplings or the brighter regions, except for this bright region that you see for the highly excited states, because that gets close to the atomic transition. But since we're interested in at least one very deeply bound clock state, here I just zoom in on the lower left corner that shows coupling strengths for the lowest 10 vibrational states. And so near the bottom of this potential, the energy structure, as always, is fairly harmonic. And this harmonic structure shows up in this characteristic checkerboard pattern of low and high transition strengths. So our first experiment with the molecular clock coherence used the state pair for the lattice coupling that's highlighted with the white rectangle. And this is relatively strong, but not quite, because it doesn't sit on one of the branches. Then for the next experiment, where we obtained that Rabi oscillation that I showed today, we chose this black rectangle for the magic lattice, which you can see is clearly brighter, and the oscillations lasted 4 times longer than in the first case. And recently, we found a magic wavelength that corresponds to this red rectangle, which actually has the best possible coupling strength. So even longer coherence times could be expected here. So we're trying to characterize this, this lattice currently. Okay, and here is just another interesting observation on magic wavelengths in the molecular clock. So ideally, magic wavelengths would be very far from any lattice-driven resonance. So these kinds of far detuned lattices are always used for atomic lattice clocks. And of course, they help avoid excessive scattering of lattice light. Based on ab initio calculations, we actually think that such magic wavelengths can exist for multiple molecular clock transitions. So in fact, that they should exist in this very convenient wavelength range near 1550 nanometers. So here we plot the predicted differential polarizabilities for 3 possible clock transitions from the deeply bound levels 2 through 4 to levels more in the middle of the potential 18 through 20. And we see that each has 0 crossings that are marked with stars. And while the exact magic wavelength values or these exact positions of the stars could shift because they're quite sensitive to details of the molecular structure that's used in the calculation, still we can be confident that we can find some magic wavelengths near 1550 nanometers, since the 0 crossings occur about every 15 nanometers. And these 0 crossings have very small slopes that are smaller than for the resonant magic wavelength that we are currently using by about 5 orders of magnitude. And this is now comparable to the situation with atomic lattice clocks. So it means that in order to achieve a clock performance at a part in 10 to the 18, the lattice only needs to be stabilized to about 100 kilohertz, and which is not too technically demanding. And we hope to investigate this kind of exciting possibility experimentally. So the prediction of these far infrared magic wavelengths also raises the possibility that blackbody radiation, which peaks around the wavelength of 10 microns or so, will be essentially quasi-magic for some pairs of clock states. And we can see this by plotting the predicted BBR clock shift for the 60 plus vibrational clock states. And it shows this non-monotonic behavior. This non-monotonic shape means that some clock state pairs, for example, 0 and roughly number 30, will experience virtually no relative BBR shift. And the same thing is shown on this color plot, which shows us the expected blackbody shifts for different clock state pairs. So while some state pairs, like roughly 15 and 60 in the upper right corner here, have relatively large differential shifts of about 1 hertz. And the same thing can be also seen on the plot. Then other pairs, such as 0 and approximately 30, have relative shifts of just a tiny fraction of 1 hertz. So if this behavior is confirmed, it'll be very exciting news for the molecular clock. Okay, and another thing is earlier today I mentioned a collisional loss of the ultra-cold strontium molecules that was still on the longer time scale than our loss of Rabi-Flop coherence. But this collisional loss is quite interesting in itself because this nonpolar van der Waals dimer, strontium-2, is a new type of molecule for ultra-cold collision studies. Formation of alkaline earth trimers, in this case, the triangular strontium-3 molecule, should be favorable, and it releases quite a bit of energy. So reaction rates of bimolecular collisions are expected to be close to the so-called universal limit. In this universal regime, the reaction rates are mostly independent of the molecule's vibrational state. Now, because of the short reactive lifetime that's expected, currently we don't know whether the intermediate strontium-4 complex that briefly forms during the collision, whether it gets rapidly excited by the trap light, as is the case for some alkali metal dimers. But on the other hand, I'll also note that if we wish to avoid collisions altogether and just to increase molecular lifetimes, then the molecules can be trapped in a 3-dimensional optical lattice for the next generation clock. So where each molecule is really by itself and is unlikely to collide with another molecule. So here is a very careful measurement of this 2-body collisional loss over time. You can see that the 1-body exponential loss, which is the blue line, doesn't describe what's going on here, but the 2-body loss, which is the red line, fits the data really well. And moreover, at the long times, we end up with roughly half a molecule per lattice site on average, which makes sense because it corresponds to kind of complete collisional loss in the sites with an even number of molecules, and in the sites with an odd number of molecules, you'd have 1 molecule remaining. And then in the inset are the measured 2-body loss rates for our molecules in their most deeply bound state and in the least bound vibrational state. So these are quite similar to each other, within a factor of 2, and are close to the universal limit that's expected at 6 microkelvin. Basically, our current implementation of the molecular clock is already precise enough to start providing some useful results for at least for the dimers of the dominant strontium-88 isotope. So the top data set is just a fairly coarse preliminary scan of the ground state van der Waals potential, and it shows all 63 vibrational states. Then the bottom plot shows the same data, but in terms of differences between our measured binding energies and the sort of partly theoretical energies that are derived from prior measurements. And our initial precision on some of the selected states that are shown with red points is more than 4 orders of magnitude higher than in previous work. And currently we are setting up the clock spectroscopy to really push the experimental limits. And so we can attain this highest precision on as many clock transitions as possible, which in practice spans the bond length, as I mentioned, from a fraction of a nanometer to several nanometers. And at the same time, our theory colleagues are figuring out all the relativistic and QED effects that play a role here. Okay, so so to conclude, here's a brief, just a brief summary. So we have created samples of ultra-cold van der Waals molecules in their absolute ground state. Then we implemented a good control of the molecular quantum states and used the molecules to demonstrate a vibrational molecular lattice clock. Now this clock now achieves a quality factor of approximately 10 to the 12 and a coherence time of about 100 milliseconds across the entire molecular potential depth, and still with room for improvement. Actually, this clock was first proposed some years ago for measurements of slow time variations of the electron to proton mass ratio, which is a nice application, but we are also excited about the application to this subpart per trillion interatomic force measurements and to setting possible constraints on new mass-dependent forces. And finally, I'd like to thank all my group members, my graduate students in this picture who are working hard in the lab to make these experiments possible. Thank you very much for your attention.
Thanks a lot for this super interesting talk. I really am impressed by the control you have over your experiment and the really nice looking results. I mean, it's, yeah.
Thank you.
I don't know. I'm not doing this anymore, like cold atom, cold molecule physics, but I did in my PhD, and I know how hard it is to get this kind of. I mean, I don't know how hard it is to get your kind of precision, but I knew how hard it is to get some lower kind of precision. So I'm how hard it was. So I'm sure there are a couple of questions, and I think Ferdinand wants to start.
Yeah, thank you very much for the nice talk. I have the question whether you could possibly shake the lattice and use this to control the interaction with the lattice. So then I think you would put your atoms into different places, so to say, and you could modulate. I think of a like a Bessel modulation index, and then possibly you can make this, use this as an additional tuning knob. I don't know. Have you thought about this also?
I haven't thought so much of using shaking of a lattice as a tool. I mean, generally shaking of the lattice is something that we think can lead to losses because that can cause what's called parametric heating. So it can cause the particles to get excited from sort of the lower trap state to the higher lying trap states and then sort of decohere that way. So if possible, we try to avoid shaking. Also, shaking can potentially lead to kind of Doppler shifts between the atoms and the probe, or the molecules and the probe, right? We try to, one of the reasons to put them in the lattice is because they're very tightly confined and they cannot move perpendicular to the lattice pancake. So when you shine a probe like this, there's no Doppler shift. But if you start shaking it independently of the probe, then you're risking picking up some Doppler shift. So for that reason, I'm tempted to avoid it, but it's an interesting thought that that maybe that you could utilize it for something useful.
Maybe also to measure the polarizability to a higher precision.
Yeah, there could be you could do that. I mean, we're pretty satisfied with our polarizability measurements. Yeah, because you know the polarizabilities are proportional to Stark shifts, for example, and we can measure those pretty well because our resolution is so narrow. Yeah. But yeah, sure.
Thank you.
Yeah.
Maybe. Well, I mean, whenever I see those kind of talks where people are measuring like additional forces, then I'm wondering whether you are also looking for oscillating things like origin beyond the standard model, like the dark matter, for example. Did you consider that?
Currently, we're not looking for any real-time dependent behavior. I think the first goal would be to perhaps create, well, the first goal is we're just working with one isotope in terms of experiment and theory, but sort of the first secondary goal would be to essentially create something like a King's plot, but for molecular vibrational transitions, which hasn't been done before. And that's something that's basically a static measurement. You're just looking if there are any deviations between sort of the spectroscopy and the theory, and you know what can you attribute that deviation to? Something expected from QED or or just nuclear size discrepancy, or it's something that you cannot explain through known physics. So that would be our first goal, and I think it'll be a while before we think about sort of time oscillating physics. I think it'll take a while to get even to the first goal.
Are there other questions? Dima?
Actually, Tanya, thanks for the very nice talk. King's plot, why can't you do it with existing data, more or less? For some other molecules, I mean, because the isotope shifts are is a big effect, right? So you probably can just build it.
I haven't seen any decent King plots for molecular isotopologues. I think strontium dimers is pretty unique because we can get data at the Hertz level now, so 10 to the 13 precision or something like that, which I don't know of any other molecule that has that. And then, so we'll be at that level. Of course, the ab initio calculations will not be at the 10 to the 13 level, but hence we're looking just not at the full calculation, but just at the isotope shifts, which should have theoretically a better precision. But I'm not aware of any other molecule that can currently provide this level.
But have you thought a bit about what this plot would mean? Because you have a very large mass. The mass shift will dominate everything, right? Compared to atomic case.
Why is that? I mean, the masses will be 84, 86, and 88 of the isotopes, and then you could potentially make mixed isotopes, but
because it's not a suppressed effect, right? The mass shift is not a
yeah, it's not that different from atomic. And I think I think it might be suppressed actually, because we are looking at a lot of transitions within the same electronic potential, right? These vibrational states, they are I mean, a lot of the effects that are common to electronic states might be suppressed because, again, we're in the same potential. And then I like the idea of using molecules for King's plots because, with atoms, every time you throw in another isotope, you also throw in an unknown nuclear size, right? It just comes with a new isotope. But for molecules, once we've exhausted all the new isotopes, then we can start mixing isotopes, and then you get new data, but no new unknown. So I think that could be very nice. Like what you've had, for example, strontium-84 dimer and strontium-88 dimer. Then you make 84-88 dimer, and it's new data, but no new unknown quantity.
Yeah, but okay, but I'm worried about the field shift being a very, very small fraction of isotope shift in the molecule.
In what sense worried? Like what problem with that?
I just have to think about how the King plots would look for a molecule when the isotope shift when the mass shift is not suppressed by anything, right? In an atom, it's a very small effect because to zeros order, you have always electron mass that enters. But in a molecule, when you have, for instance, a vibrational state, right? The mass it just enters directly without any suppression.
Yeah. Well, I mean, I think the basic vibrational physics is well understood. So we're still looking at sort of high order effects that are dependent on the nuclear mass. And for that, it's actually nice to have a heavier atom because these effects are a little bit smaller. This kind of electron to nuclear mass ratio is a bit smaller in a heavy molecule than in something like hydrogen, for example, where these corrections are big. But yeah, I mean, I'll be happy to discuss King's plot with you later because no one's really analyzed this for molecules, and we'd be kind of doing it for the first time.
Cool. Are there other questions? Mustafa, what's up?
Yeah, great talk. I have just a basic question. How do you control the number of molecules inside of the lattice? Or because I mean, due to the dispersion forces between the molecules, I guess you get some frequency shifts depending on the density, right?
Yeah, so our molecules are non-polar. They're interacting very weakly. They're kind of like atoms. They're not really interacting. And also the density is pretty low. So in these pancakes, we might have not more than 100 molecules per pancake, and they're pretty spaced apart. So right now, if even at our high resolution, if we halved the density, we wouldn't see any shift even at the Hertz level. So the shifts are not dominating right now, very small.
Okay, thank you.
You mentioned trimers, and when I hear trimers, I think of Efimov states. Is that something that you have looked into? Would that, I mean, does it exist for strontium?
I don't actually, strontium-88 happens to have an ultracold scattering length of about 0. So I don't think strontium-88 would be your atom of choice to see this sort of interaction physics. So when I say trimers, these are literally bound molecules. They're properly bound molecules, strontium-3, that are nice and stable, like a triangle. So yeah, FMO physics you would not do with this particular atom.
Great. And maybe as a last question, what are your experimental challenges at the moment? I mean, what are you working on? How are you trying to improve your system?
Yeah, so the main challenge is that we're trying to do kind of clock physics, but we are not in Boulder, Colorado, or some place like that, or PTB or something like that. So we don't really have a good reference metrology. And once you get down to a part per trillion or so, right, part in 10 to the 12, then, you know, we use, you know, just for absolute frequencies, we use just some rubidium clock off the shelf that's tied to a GPS satellite. But, you know, again, it bottoms out at 10 to the 12. And so then if you want to have your absolute frequencies at better than that, we don't really have a way to do this. So, you know, now we're just trying to get the relative systematics. So just compare, you know, molecular transitions to molecular transitions without any Hertz involved. So that's something we can do by, you know, removing as much noise as possible. But then for absolute metrology, I think it would be hard to do it here. But then also for this experiment, it's not super critical for us to know exactly how many Hertz everything is, because we can just do ratios of molecular transitions.
Great, thanks. Maybe while you guys think about a last question to ask, I will advertise next week's quantum seminar. It will be given by Professor Ilya Gerhard. He's professor now at the Leibniz University of Hanover, and his talk is called "Cool Experiments with Hot Atomic Vapors." It suits him well to have such a catchy talk title. Any last questions? If this is not the case, then let's thank Tanya again for this nice talk, and thanks as well for getting up that early. I'm not sure whether that's early for you.
A bit early.
Depends on your lifestyle, I guess. So yeah, thanks a lot, and we hope to see you at some stage here in Mainz.
Yeah, I look forward as well. Thank you.
Thanks a lot. Have a good week, everybody.
Yeah, thank you very much.